Welcome to the Salmon Runs YouTube. Enjoy the video.
You start by labeling every mesh loop and assigning a mesh current to each. This immediately gives a sign convention, so equations are consistent. Once done, mark resistors shared between adjacent meshes and note which voltage sources are interior versus boundary. You should convert dependent sources into their controlling variables early and combine series resistors when they lie entirely inside one mesh. Doing that reduces algebra later. This sets you up to write Kirchhoff voltage equations cleanly and without ambiguity. Now write a KVL equation for each labeled mesh, summing voltage drops around the loop. For resistors unique to one mesh, use R times that mesh current. For shared resistors, use R times the difference of the two mesh currents, EI minus IJ, to capture opposing directions. Include sign conventions for voltage sources consistently. For dependent sources, substitute their expressions. Once you have all equations, collect like terms, so each equation reads as coefficients times mesh currents equals a net source term. Ready? Solve the resulting linear system using your preferred method. Substitution works for two meshes, while matrix inversion or Kramer's rule is efficient for 3 or more. Once solved, convert mesh currents to actual branch currents by summing or subtracting mesh currents where meshes overlap, and verify voltage drops across key elements. If results seem off, retrace sign choices and the shared resistor terms. Most errors come from an EI minus IJ flipped or a source sign reversed, so correct that and resolve the linear system.
Thanks for watching. Consider subscribing if we helped you.